Okay, in the 2020 10A problem 6, which was also the 12A problem 4, how many 4-digit positive integers, that is, integers between 1,000 and 9999 inclusive, which should be obvious, having only even digits are divisible by 5? Okay, well, if you can have only even digits and be divisible by 5, it's going to have to end in 5 or 0 for the 5, but you can't have the 5 because it's even. Therefore, it must end in 0. So then we have to say how many 4-digit, we have to have only even digits in these 3 positions. So in the first position, you cannot have 1, you have to have 2, 4, 6, or 8. You also can't have 0, there's 4 choices. The next 2, you can have 0 through 8. That's fine. That's 0, 2, 4, 6, 8. That's 5 choices and 5 choices. 4 times 25 is 100. Continuing on to the 2020 10A problem 7, which was also the 12A problem 5. The 25 integers from -10 to 14 inclusive can be arranged to form a 5 square in which the sum of the numbers in each row, the sum of the numbers in each column, and the sum of the numbers along each of the main diagonals are all the same. What is the value of this common sum? Don't start making a 5 by 5 grid. Think about it. If it's a 5 by 5 grid, you're going to have 5 rows of 5, all of which must be equal. And so whatever the sum is of all the numbers in the whole thing, I must be able to divide that sum by 5 to get the sum in each row. That way the sum is equally distributed amongst the rows. So we can just say that from -10 to +10, the sum is 0. We really need to add 11 to 14, which is 4 tens, which is 40, and the sum of 1 through 4, which is also 10, to get 50. And then we can just divide that by 5. That's the net sum of the whole thing. It must be that there's 10 in each row and column. Okay, and on to the 2020 10A problem number 8. What is the value of 1 plus 2 plus 3 minus 4 plus 5, 6, and 7 minus 8? Basically, it looks like all the multiples of 4 are being subtracted while everything else is a normal summation. Well, we can probably try and do it in groups or something like that. That's fine. But the fastest way is probably going to be just to add up all the numbers from 1 to 200. The sum of the numbers from 1 to n is equal to n times n plus 1 over 2. These are called the triangular numbers for reasons you can look up elsewhere. So 200 plugged in is 200 over 2 times 201. That's 100. I get 20,100. Now, the thing is, though, I don't want the multiples of 4 in there. So we have to subtract them once to get back to not having them, and then we have to subtract them a second time because they're actually negative values. So you want to subtract -4, -8, -12, all the way to -200. Just factor out the 4. And you'll get -4 times 1 plus 2 plus all the way to 50. This is the same setup as this, so it's 50 times 51 over 2. This goes in 25 times the 4 is 100. That becomes 5,100 but negative. But that's only getting rid of them once. We have to double it to get rid of them twice. So we will subtract 10,200. If you subtract the 200 first, you'll be at 19,900, and then subtract 10,000 more to get to 9,900. Continuing on with the 2020 10A problem number 9. A single bench section at a school event can hold either 7 adults or 11 children. When n bench sections, capital N, are connected end to end, an equal number of adults and children seated together will occupy, and this is important, all the bench space. What is the least possible integer value of n? Okay, so what we can think of is we should probably target the least common multiple of 7 and 11, which is 77. You might be thinking, that's not the answer, by the way. You might be thinking that, one adult can equal 11/7 of a child. Is it possible then that, some children and some adults occupy the same bench, together? And we don't really have to worry about that because it says all the bench space will be used. So there'll be no space that's like, gaps between the end of the bench where, multiple children and adults sat on the same bench. We don't have to consider that in this problem. Okay, so if we target 77 adults and 77 children, I simply divide by 7 to get 11 benches for the adults and divide by 11 to get 7 benches for the children. This will produce an equal number of children and adults. I do get 18. The fact that A is here and it wanted the least possible integer value of n, it does worry me slightly, but I think we're okay. The answer is B. Continuing on with the 2020-10A, problem number 10, which was also the 12A problem 7. 7 cubes whose volumes are 1 through 343, which are all the perfect cubes from 1 to 7, cubic units are stacked vertically to form a tower in which the volumes of the cubes decrease from bottom to top. So I start with the largest volume in the bottom and it increases from there. Except for the bottom cube, the bottom face of each cube lies completely on top of the cube below it. Let's try to get an idea of what this looks like. Just draw a quick sketch of a cube. Okay, and then on this cube is going to be another cube, right? And so it's going to sit like this. Something like that, right? And so you can see that the top cube lies completely on top of the bottom cube. Okay, what is the total surface area of the tower, including the bottom that's down here in square units? Okay, the first thing we have to do is that we have to find the edge length, which we said was 1 to 7, and then you're going to use that to find the surface area of the bottom cube. It'll simply be 49, the area of one face, times 6, which is 294. Okay, but what happens when I attach this block here at the next block up? Basically, this block here is going to also be 6 sides, each with 6 squared, which is 36. However, one of those sides is facing down, so we don't count it in the surface area. And then it covers up an equal space on the 7 by 7 by 7 cube, so you're losing an additional area of 36, and you really only have 4 times 36. The problem basically breaks open from here. You simply have to consider that all of the cubes as you go up are going to have this same problem. So when I put the 5 by 5 by 5 cube on here, it will cover an equal space on it as well as on the cube below it, the 6 cube. So we can just add 4 times 25. We'll just do this. Plus 4 times 36 plus 25 plus 16 plus 9 plus 4 plus 1. 10 and 20 is 30. And this is 61 to give 91 times 4 is 364. Add 294 to get 8. 5, carry the 1, 658, which is answer choice B. Are we sure it's going to end that way at the top? Think about the top block, right? It's a 1 by 1 by 1 cube, and it's going to lose one face of itself, and you're also going to lose one face on the 2 by 2 by 2 cube. So it makes sense. This does check out all the way to the end. We can be sure the answer is B.